All right, welcome to Module 1, 3 Basic Concepts. In this video, we're going to talk about grammars and automata. All right, so grammars are used to generate languages. A grammar is a quadruple or a four-tuple. The four-tuple is made up of the following. The V stands for variables. These are usually uppercase letters. It's a finite set, and the variables are usually uppercase letters. Sometimes it might be an S or an A or a B. The T stands for terminal symbols. These are usually lowercase letters and they're usually the alphabet. So like we've been seeing before, we have A, B, maybe C. Those would be the terminal symbols or the lowercase letters or the alphabet. The S is the start symbol. So many times we will probably use S to stand for the start symbol. And just take note here that the start symbol is one of the variables. So most likely we will use S for the start symbol for most examples, and S is one of the variables. And then there are a set of productions. Those productions are how you transform one string into another and generate the languages. And so it's best to understand that by looking at examples. The productions have a left-hand side and a right-hand side. We will definitely be learning more about grammars because the different types of grammars and the rules on different types of grammars relate to different types of languages. So let's just practice now an example of a grammar. So if you take a look at it, you can see the set of variables here is just an S, and you can see that the alphabet is A, B, and the start symbol is S, and then these are the production rules. The production rules are what is used to create and generate the strings that are in the language. So let's run through a couple examples running these production rules and try to figure out what this language is. So you can start with S. That's a start symbol. And here, if this one right here where you go to the empty string, then that would mean that this language includes the empty string, because you can start with S and go to the empty string. So we know that the empty string is part of this language. But let's try some other productions starting with S. And we can go to here, A, S, B. And from there, we can replace this S right here with the empty string, so that would just go to A, B. So we can see that we're just replacing this S with the empty string, and you can see that A, B is one of the strings in the language. Let's try another one, S. All right, and this time we're going to do A, S, B, and then we can have A, but we will replace that S with a oops, I wanted to do it purple, with a A, S, B, and a B. So now we could keep on going, but I'm going to stop here. You can see that each time you can follow the production, and for each S you would just put an A, S, B, till eventually we would just have A, B, B. This would also make A, B, 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 A, 4 A's and 4 B's. So we know that this language is A to the N, B to the N. As you can see right here, the language is A to the N, B to the N, and N would be greater than or equal to 0 because it does include the empty string. All right, let's look at another one. Here's another one. This language is A to the N, B to the N plus 1. Again, the grammar, this is not correct because here the variables shouldn't be just S. It should be A and S. It's not very neat. I'm going to have to fix that. So the variables here are S and A. So there's two variables. The alphabet is A and B, and the start symbol is S. And so you can apply the different productions, and you can also see that this does not include the empty string because even though it says n is greater than or equal to 0, this string will have at least one B. So even if you started at your start symbol and went to this production right here, and then got rid of that, you would still see that B is one of the is in this language, just the single letter B, which is obvious from looking at the description. All right, let's try another one. Let's try all strings that start with A and end with B. So this is all strings that start with A and end with B. So I'm also going to make this assumption that our alphabet is just A and B. And so let's develop a grammar in which all strings start with A and end with B. All right, so that means that it will not include the empty string. So our start symbol will not go to null, but our productions will be as follows. We'll start with a production that begins with an A, and we're going to have to use another variable, and ends with a B, because this does not include the the empty string, and it has to start with an A and end with a B. But then you can have any combinations in between. So if you can have any combinations in between, what does that mean? That means that you could add extra A's, or you could add extra B's, at any point, or you could end there with just AB. So if you do a few of these productions and create some strings, the first one we would start at S, and then we could do A like this. Now of course, if we went to the empty string here, if we replaced A with the empty string, then we would have just the string AB. But let's do some other productions here. Let's try here. We can go A, and then we would put in the A, and then we can try AA, and we could put a B in there. So you can add any number of A's, add any number of B's, and then eventually you would put in, let's add another B. So we would have A, B, and we want to put another B in there. So any number of strings that start with A and end with B is part of this language. So AB, we could also, instead of adding A's first, you could add B's first and then A's. So we could try, let's try up here, A, B, then we could just put some B's in there and put a B in there and then an A in there. So to do that, we would just go like this. So we added a B, and we can add an A, or add another B. So again, then eventually we put in the, we get rid of this A, so A, B, B, B is in there, or we could add another A. So A, B, B, A, B. So again, just as long as it begins with an A and ends with a B, then it is in this language. All right, we'll do one more. Okay, now let's try another example. And by the way, these examples are very similar to your homework assignment. All right, so let's do one that is all strings with at least 3 A's. All strings with at least 3 A's. So our alphabet is A and B, and we will come up with our variables, and our terminal symbols will be alphabet letters. So let's get started. So we can tell right away if we have to have at least 3 A's, that means that the empty string is not part of the language. So we will start by generating 3 A's, and then we can add any number of other A's and B's anywhere we want. So if we have an A and an A and an A, right? So it doesn't mean where the A's have to be in the string. So we could have an A or a B here, we could have an A or a B here, we could have an A or a B here, or we could have an A or a B here. And then our variable A would either add an A, add a B, or not. So this is an example of a string with at least 3 A's. Okay, so now I'm just going to talk a little bit about automata. So automata is an abstract model of a digital computer. So automata is plural, automaton is an abstract model of a digital computer. We defined it already, but let's just refresh. It can have input over a given alphabet, so you can give it input. It will read the input. It doesn't modify the input, and it reads the input one symbol at a time. If the automaton reads the input and decides if it's accepting or not accepting, which is what we're going to be doing with DFAs and NFAs, then that is called an acceptor. If the automaton reads input and produces output, then that is called a transducer. So in Module 2, we are going to start to learn about DFAs and deterministic finite acceptors. The reason they're called acceptors is because they do not change. They don't have an output. They just either you just take a string and you run it through the states of the DFA, and if it lands in an accepting state, then it is part of the language, and if it does not, then it is not part of the language. So that's basically how DFAs and NFAs work, and we will work on that in the next module. So just as a reminder, we are going in this class, we are going to be going through different languages and the different automaton for each language. The first language we're going to start on in Module 2 will be regular languages. We will start on grammars. We will be doing right linear and left linear grammars, which means that they're going to have very specific rules on the productions. And the automaton for regular languages are DFA and NFA. So we will begin this in Module 2.